This is the sixth and final part in a series of videos on division by zero. In this video, we'll explore some potential further developments and applications of zero numbers, hypercomplex numbers, and metacomplex numbers. To some extent, this exploration will be rather speculative. But at the end of the series, it's maybe not a bad idea to look beyond the horizon of the developed theory. Let's begin by examining what happens when numerical values approach infinity. What lies beyond infinity? Consider again the function 1 over x as we did in part 1. As x approaches 0, the function values go to infinity for positive x values and to negative infinity for negative x values. That's why we said that 1 over 0 is undefined. However, this is only the case for real or complex numbers. When we extend the numbers to hypercomplex numbers, the graph of the function 1 over x for real numbers x lies in the complex plane. But when the function values reach infinity and negative infinity in the complex plane, the function value becomes equal to z in hypercomplex space. You could say that it is as if the function falls back into z. It's as if beyond infinity, the complex plane falls back into the zero number axis, not just into the zero unit, z. This becomes evident when we plot the function 5 over x, for instance. For x equal to 0, the function value in this case is equal to 5z. The function falls back higher into the zero axis, into 5z. Similarly, we can say that a set of numbers transitions into another set when one of the two coefficients, a, b, c, or even d, becomes 0 or infinite. Let's consider a few cases in the hypercomplex space. When the value of c in a hypercomplex number h equal to a plus bi plus cz becomes 0, the number becomes a complex number, a plus bi. It's as if it is projected onto the complex plane c. When we set the c coefficient to 0 for all numbers in the hypercomplex space H, it is as if the entire set is projected onto the complex plane, as if the set H collapses into the set C. Thereby the dimensions are reduced from 3 to 2, from a space to a plane. Conversely, when the zero numbers of the form bz reach the origin, meaning when b becomes 0, it's as if the z-axis collapses into the origin and spreads into the complex plane. The one-dimensional z-axis transforms or transitions into the two-dimensional plane of complex numbers. I use the term collapsing when the number of dimensions decreases in transition from one set to another, and the term spreading when the number of dimensions increases. This way, with a little fantasy, it is as if numbers can travel from one dimension to another. Let's now explore some possible further developments similar to the theory of zero numbers. By including zero numbers, it becomes possible to perform division by zero, an operation that is undefined or leads to contradictions in other cases, with real numbers, for instance. But there are other forbidden operations that can potentially be enabled in this manner. Take logarithms, for example. We all know that the logarithm of negative numbers does not exist. The logarithm of 0 is also undefined in the set of real numbers, but I will omit that case for now. The logarithm of, for instance, -1, -265, or -pi does not exist. This becomes evident when we have a look at the graph of a logarithmic function. Only for positive x values does this function have meaningful values. In the domain of negative x values, indicated here in red, the function has no value. But what if we introduced the L number unit, the number L equal to logarithm of -1? At that moment, a whole new set of numbers arises, the set of L numbers of the form kappa L, where kappa is a real number. Then it becomes possible to work with logarithms of negative numbers as well. The detailed development of this theory is beyond the scope of this research. I only want to briefly outline 2 points. First, for a positive real number a greater than 0, we have the logarithm of -a is the logarithm of -1 times a, which is the logarithm of -1 plus the logarithm of a. So that is L plus the logarithm of a. And secondly, when we combine the set of L numbers with the 4 sets already developed, we obtain numbers in 8-dimensional space that we call L numbers. I would gladly leave it to someone else to further develop this theory. To conclude this series, let's briefly discuss possible applications of zero numbers. It is nice to be able to divide by 0, but what can we actually do with it? In other words, do zero numbers offer practical applications? Perhaps they merely add to the arsenal of abstract concepts within mathematics, but even then they could be useful, at least for nerdy mathematicians. It's worth noticing that the theory of zero numbers is not the only possible approach to division by 0. Throughout the history of mathematics, numerous theories have been developed in this regard. I would like to mention only the work of Professor Saburo Saito, who kindly pointed out in a comment on the first 3 videos in this series some journals and publications on this topic. The future will tell if zero numbers can make a contribution in this field. Perhaps zero numbers could play a role in quantum mechanics or theoretical physics. It seems not completely impossible that they might be useful in research on vacuum energy, for instance, or singularities such as black holes or the Big Bang. Black holes are where God divided by 0 is a statement attributed to Einstein, although it's not his. In quantum mechanics, complex numbers are also required, for instance, in the Schrödinger equation. I am not a physicist, so I don't know if zero numbers could also play a role in physics. Only the future in space-time will tell. With these final remarks, we have reached the end of this series. In the description of this video, you can find a link to the article I wrote on division by 0. Please leave your remarks in the comment section below. Thank you for watching.